Welcome to Peninsula Seniors Out and About. We're at the Western Museum of Flight in Torrance. Let's go see what Cindy has for us today.
Welcome everyone to the Western Museum of Flight. I'm Cindy Maka, the director. Occasionally in life, a keen intellect finds the happy coincidence of one's vocational duties encompassing a particular subject that is also a matter of deep personal interest. When that happy coincidence occurs, the results can be quite fascinating. That has been the case with today's program. All three of these fortunate conditions have converged in the person of Joe Orr, his work as an Air Force historian, and the intriguing history of one of the Cold War's most productive false starts, the B-70 Valkyrie. Fortunately for us, we are about to experience the benefit of that happy convergence. Ladies and gentlemen, it's my privilege to introduce to you Joe Orr.
Thank you, Cindy, for that gracious introduction. You are here to hear about the B-70. I equate this to one of the most significant technological jumps of the 20th century because it was designed as a high-speed, long-range bomber. The program was not without its detractors. It had a lot of political issues. And when you're dealing with the military, you're always dealing with everything is political because everything flows from our friends in Congress. But after World War II, the Army, and later on in 1947, the Air Force, began looking at how can you proactively build your Air Force. We didn't want to get back to the situation we were in at the end of, or in the 1939, 1940, where we were using equipment that was 10, 15 years old in many cases. We wanted to get stuff that was modern. The Army did not want to get back into that situation where if there was a war, they were going to have to start developing new systems now. They wanted to have the new systems already developed, already in use. At the end of World War II, the primary bomber was the B-29. By the early 1950s, they'd put some modifications in that, and in fact, solved a lot of the problems of the B-29, but the problems were solved. But solving the problems was such a major deal that they basically came up with a new airplane. They called it the B-50. They came up with the B-36, which was a propeller-driven plane, big monster. I don't know how many of you have seen one. I've actually had the pleasure of being in the cockpit of a B-36 at the Air Force Museum. Don't ask me how I did that. I think the statute of limitations is over, but we'll see. By the late 1940s, they were experimenting with jet-powered bombers, but because the jets at that time were very underpowered, the jet engines had not come along fast enough to keep up, so the bombers were quite small. And then finally, the B-52 came out in the mid-50s. Now, as each successive bomber came into progress, as each successive fighter came in, what they were doing was, okay, this one's here now. What's the next one going to look like? What's the next one going to look like? How do we go from here to the next? And they were literally talking with industry people to get their ideas of what the technology was doing, how things were going to go. Now, the B-52 began service in 1955. So the Air Force is looking, how are we going to replace this one? Now, the B-52 had a single advantage over everything else. It carried more bombs than anybody else. Now, it was not as fast as some of the fighters, but it was faster than the other bombers. And it had a huge capacity. Because of that, they were very well suited to fight the war at that point in the 1950s. But again, you got to remember, there's a lot of political stuff going on in the background. We were dealing with, okay, how are we going to approach a nuclear war? What are we going to do with a conventional war? How are we going to respond to somebody coming and attacking us or attacking one of our allies? A lot of that was going on in the background while we were doing these weapon systems. Now, the Soviet Union had jets that could fly faster than anything we had, especially the propeller aircraft. In the Korean War in the 1950s, we had B-29s and B-26s that were flying bombing missions, and they had to deal with the fighters, the Russian fighters. And a lot of these fighters were not flown by North Korean pilots. There were Chinese and Russian pilots in there that were doing a lot of damage to our stuff, but we just couldn't compete as far as bombers were going. In 1956, the Air Force came out with its B-58. Now, B-58 was a Mach 2 bomber. At that point, it was the fastest thing in the air. It was significantly smaller than the B-52, however, and it had a smaller payload. However, a side note, the B-58 still holds the record for weight to altitude. I think it was 50,000 kilograms, taken up to 50,000 feet in a specific time period. So they had the capability, but they just didn't have the storage for bombs. They had a big pylon thing that's set up underneath the bomber, and they could load that with all kinds of stuff. But if you were flying a long-range bombing mission, that was your fuel tank, so it really didn't help a lot. Military strategy in the 1950s was, for bombers at least, they began looking at what they called the dash. Okay, so they would fly at a subsonic speed in friendly areas. Once they came to a place where they would cross over into an enemy area, they had to zip up to high speed, and they would dash in, drop their payload, and then fly back home. The problem is that anytime you get above a certain flight level, particularly when you're talking sonic and supersonic ranges, your fuel consumption rises. And the faster you go, your fuel consumption does not rise at a straight line, it's exponential. So what you're using down here at, say, Mach 0.5, and it runs along slow, and then all of a sudden you're at Mach 2, and your fuel consumption is way up here. So how do you develop a plane that's large enough to carry that much fuel that can go that speed for the time that it's going to have to go? This was a very significant problem. Now, the B-58 could fly 2+ Mach. So they were using the B-58 kind of as a springboard, saying, here's what we can do now. How can we do this with a bigger plane, bigger payload, even faster? The Air Force issued a request for a high-altitude, long-range bomber with Mach 3 dash capability in 1955. They wanted to be able to carry a nuclear or conventional payload that was equal to or larger than the B-52. 6 companies were contacted, only 2 responded, Boeing and North American. Now, both of their initial designs utilized a large central aircraft that had wings off to the side. And the wings off to the side were detachable. They had large fuel pods on them, and they would use the fuel in the outside wings to fly to the area where they were going to start the dash. Those wings would fall off, and they would zip up to Mach 3 and go in there. The problem was that these planes were so large that they became cumbersome. The commander of the Strategic Air Command came back and said, well, wait a minute. We just rebuilt all of our facilities, all of our hangars, everything for the B-52. everything is B-52. Now you want me to start all over again. You're going to have me rebuild all these hangars to be twice the size or more so we can handle these planes. That was a problem. They also had some interesting things. They had huge engines, and they used a boron-type fuel. It was actually a specific formula that had boron infused in the fuel, so it would increase their capability by adding some thrust augmentation to just regular fuel. Well, boron's expensive. It's corrosive. All kinds of problems with that. So they kind of looked at that, and the Air Force said, well, thank you very much, but we really want something different. What can you give us? Well, about that same time, mid-1950s, scientists at the National Advisory Committee for Avionics, which was the forerunner of NASA, were doing some air tunnel or wind tunnel tests on reentry vehicles for missiles. What's going to happen when these things come back in the atmosphere? And they discovered that what you would think as conventional knowledge was not happening. There were anomalies going on. Things were not as they seemed. And they discovered a new, it's not really new, but they discovered a process that they called compressive lift. As a cone-shaped object flies through the air at high speeds, it builds up a pressure wave of air in front of it, just like a speedboat does. If you think about, if you've ever ridden in a speedboat, and I assume most of you have, when you push the throttle forward, it sits there and goes nothing, and it just kind of labors along until it lifts up and gets on that bow wave, or that wave that's being pushed ahead of it. Once it gets up on there, off you go. Well, compressive lift was a study that NACA did, and they put it out there, and North American people looked at it and said, if we took this principle, can we design an aircraft that uses that compressive lift to ride on the shock wave? Now, in order to do that, they had to design a long, skinny front where the cockpit is that will split the air and cause that shock wave to come back and meet the fuselage at some point, so that they can generate that lift and bring that plane up. And that's what they did, and that's what they came up with, the B-20 or the XB-70. Now, before I go any further, I need to talk a little bit about the video that's kind of going here in front of you. Right here, what you see is the B-70 coming in for a landing. They took off, they did their stuff, and they came back and they flew the landing. Now, if you'll notice, just as it goes by, you will see right about there, you see that T-38 flying next to it. The T-38s, whenever the B-70 flew, there always had to be a chase plane. They had to have these people because they were so big, and they had some problems with their hydraulics, so they always had to have somebody who would look at what was going on as the plane was taking off and landing, because that was the point where the problems usually happened. And if you think about it, taking off and landing is when you don't want problems to happen. One of the interesting things, you see that little school bus looking thing? That was kind of their ground crews were in there, and they would kind of watch what's going on and give the air crew an idea of where they were, if things were working correctly, if things were going wrong. That school bus is still on Edwards. It's at the Boneyard, which is owned by the Flight Test Museum. I'm trying to convince them to take that down to Dayton, Ohio, to the Air Force Museum, which just opened a new research and development hangar and the XB-70 and some of the other research development planes that they have are in that hangar. I think that would be a great addition to that display. When they were developing the B-70, the Air Force said they want to go Mach 3, carry a payload that's large as a B-52 or bigger, and we want it to be able to fly long distances. And we want it to fly at 70,000 feet. So the industry people kind of shook their heads and said, they want what? They put it together. Obviously, there were things that had to be developed that had never been developed before. That's where I talked about that technological jump. Because first of all, you're flying at 70,000 feet. What's the atmosphere like at 70,000 feet? You can't breathe, it's cold, it's ugly. What do you do? Oh, by the way, the Air Force said, and we want this capsule, the crew capsule, to be designed so that they can operate in their shirt sleeves. No pressurization, no pressure suits. They want to be able to just get in it and fly. How do you do that? Well, they had to come up with, first of all, what if something happens at 50,000 feet and these guys have to punch out of the plane? So they had to come up with a new egress system, new escape system. Now, the B-58, again, was the starting point, and they had a capsule already that they used for escape at Mach 2. So they just developed this a little bit further. They took it a little further and made the escape capsule a clamshell thing where the seat was, and it was up over the top of you, and if you had to escape, you would pull it down and it would clam together and it would kick you out the top of the plane, and you would not be damaged by any buffeting winds or anything as you came out of the plane. What's interesting about this is it also had a flotation ability. It had a survival gear in there. If you escaped or ejected over water, it had a fishing kit, fishing tackle, and you could fish, and it floated. It floated just like a boat, they said. I don't know. They had to come up with new fuels, okay? JP4 was the standard fuel at the time. JP4 evaporates at minus 40. It's the flash point, minus 40. Okay, if you're at 70,000 feet and you have low pressure already, that evaporation point goes down, which means your fuel tanks are going to be in constant fumes. Now, anybody who knows anything about fuel knows that it's the fumes that burn, not the liquid. So basically, you now have a huge bomb full of fumes. So they came up with a new fuel. They developed JP6, which was designed specifically for the J93 engines, which is similar to the JP5 Jet A. It's a little bit thicker, lower freezing point, it's a lot more stable. And interestingly enough, they incorporated a nitrogen injection system into the fuel cells. So that space between the water and the top of the tank, instead of being full of air and fumes, they injected nitrogen in there, and that nitrogen reduced the chance of explosion. They also used the fuel. They had a heat transfer system for the cockpit, and that would transfer the heat from the cockpit back through the fuel cells, and the fuel cells would cool down the air and keep the cockpit area nice and cool. The wingtips on the planes could be dropped down 25 degrees and I believe 65 degrees, and literally trapped the shock wave. You know, remember as it rode, as that nose was out there and it split the air and it caused that shock wave would hit the fuselage and would lift up the plane. Well, if you drop those wingtips down, it catches more of that and gives you more lift. They had the vertical surfaces, more vertical surfaces with those wingtips down, gave more stability, and it also overcame a center of pressure phenomenon. As the plane gets faster and faster, the center of pressure moves back. That means as the faster you go, it pushes the back end of the plane up, pushes your nose down. Now, at 100 miles an hour, it's probably not going to be an issue. But at Mach 3, which is approaching 2,000 miles an hour, it's an issue. You don't want your nose to go down. You want to keep it up. So as they dropped those wings, it kept that center of pressure forward, and it kept that nose from dropping. They also had the control surfaces on the wings. They had 6 control surfaces. 2 of them were on the wings that tipped down, on the wingtips. When those wingtips tipped down, those 2 control surfaces were locked in place, and they just used the 4 on the tops. It kept a lot of the drag down. It really, I mean, this plane was amazing. And remember, it was designed in the 1950s. Okay? Now, they had one major problem that was the biggest problem to overcome. As these planes got faster and faster, even at 70,000 feet, there's enough oxygen in there to cause friction. And they had a lot of issues with what do we do with this thermal barrier? At that time, everything was made out of aluminum. B-58 was made out of aluminum. As the temperature gets up around that 700 or 800 degree temperature, aluminum melts. So your skin of your airplane is literally going to peel off behind you as you're going at this speed, and they had to overcome that. What they came up with was a honeycomb design. Now, over on the table over here, there is a piece of the skin that a friend of mine found out at the crash site. Actually, it's part of the debris field, which was spread over several hundred square miles north of Barstow. And if you look on the backside of it, you can see the honeycomb design where the steel was in there. And there's also a little model, looks like an XB-70 that's stamped out. It's stainless steel. Now, half-inch stainless steel is very heavy. In fact, I have a little piece of the Alaska pipeline that's half-inch steel that weighs about 10 pounds. Okay? Now, if you built the entire plane out of that half-inch steel, it would never get off the ground. It's going to be way too heavy. So what they did was they designed a way the North American engineers designed a way to take 2 really thin strips, like thinner than aluminum foil strips of stainless steel, and they would put them together with a bonding agent and this honeycomb steel between them, and they would put them in a press with high temperature, high pressure, and it would literally weld those pieces together. Now you have a half-inch steel that weighs nothing compared to what regular steel would weigh. Now, another thing that this did, besides being strong and light, there's air in the middle. And anybody who's ever lived in Alaska knows that when you build your house, you put your insulation in there and you fluff it up to get lots of air pockets. Because air is what's causing the insulation, not the material. It's the air pockets that insulate. So this stuff was not only strong, lightweight, but it was insulative. It created insulation for the plane. However, to do this, they had to develop new technologies. They had miniature welding machines. They had a particle beam welder that they had to use to get into those hard-to-reach places. And the leading edges and areas of higher temperature on the plane were made of titanium. Now, this was the first time that an aircraft had ever married titanium and steel or aluminum into a single product. And in fact, the American Society of Metals awarded North American for their development of the use of titanium in building the plane in 1959. Now, this plane had 6 GE J96 engines. Each one developed 30,000 pounds of thrust. They're only the second largest plane engines ever developed. The largest were used in the SR-71. As this plane was flying and being developed, they came up with a lot of innovative ways to get rid of the heat. One of the ways was the white paint. If you'll notice that white, everything is white. That's called ablative paint. Now, ablative paint is a specially designed paint that sucks the heat off. It actually is a way of removing the heat from the plane and putting it back out into the atmosphere. And one of the slides actually shows the J96 engines, the 6 of them in back, and if you look real carefully at the vertical stabilizers, you will see that that paint has peeled off. So as the plane got really fast, it would actually, even though it was good, it would still peel the paint off. The air intakes on this plane, now when you look at the model over there, it's kind of hard to see, but the air intakes on these things were a special design as well. As you get really fast, the air coming in the air intakes is pushing against the engines. But as that air goes much faster and faster, it blows through the engines before it can do any good. So they had to have a way to slow down that air. Those intakes on each side, one fed the 3 engines on the right, one fed the 3 engines on the left. They could actually throttle those throats down. Now, if you've ever been fishing on a river and you've been on the rapids, generally the river is real narrow and it's going real fast, and at the bottom it opens up into a big pool and everything slows down. That was basically the theory behind this, was they would slow that, they would push those inlets in, and then they would expand them out on this side, and as that air came through, it would slow down. And that way they were able to keep the pressure at the front of those engines at a constant rate so that they were always being fed by air. Now the design also took advantage of that shock wave that they were riding on, because that shock wave hit right in the front of the splitter between the right and left air intakes. And as those shock waves that get going, they could be bouncing back and forth down that air intake, and that would also create pressure. And in fact, that shock waves were part of the fuel economy of these planes, because that shock wave would create the compression that ran the engines rather than the engines having to create their own compression. The first plane rolled out of Palmdale at the plant in May 11th of 1964. And it was a media circus. Everybody was there. I think they really wanted the Russians to know what we had. However, timing is everything. And at this same point, long-range missiles was the way the government was going, the Air Force was going. They wanted long-range missiles. They wanted to be able to spend less on air crews. They were easily stored. They didn't have to do as much maintenance on them. They were nicer to, one time and done with them. So, even though the commander of the Strategic Air Command argued that I do need people in the planes, so if something happens, I can recall them, I can't recall a missile, Congress still said, no, we're going to go with the missiles. The capabilities of the B-70 did not outweigh the missiles. We could launch a missile and have it be over a target area in a matter of minutes, where even the fastest B-70, it would still be hours. Operating costs were high, so they decided that they're going to go with the B-52, stay with the B-52 as the primary bomber, and the XB-70 became a research vehicle. The initial flight took place in September. By the time the second XB-70 rolled out in June of 1965, 13 test flights had been done. Only one had been to Mach 3, and it's the only time the number one vehicle ever got to Mach 3. Apparently there was a lot of flutter, chatter, whatever you want to call it. As the number one vehicle approached Mach 3, there was some problems with it. That was solved in the second one. One of the primary problems was that they raised the angle on the wings by 5 degrees. It's only 5 degrees, but that solved a lot of their chatter problems. The pilot flew the plane. The co-pilot did everything else. He managed all the tests. He took care of the fuel transfer to make sure everything was, the center of gravity was correct. He also manually operated the throat on the intakes on the number 1 plane. By the number 2 plane, that was all automated, but still had a lot of work to do for the pilot or the co-pilot. The original number 1 plane had 19 test points on it. The number 2 plane had 230 test points on it. So it was a much more capable plane. The entire bomb bay was full of testing, recording devices. It was set up perfectly for doing a lot of this stuff. So what did they do? Well, back in the 1960s, the government was doing a number of projects on shock waves, on sonic booms. What happens to sonic booms? They would build a house out in the middle of the desert. They would fly this thing over it real fast and it would boom. And then they'd go back there and they would check the house. What happened to the house? That sonic boom as it went by, what kind of damage did it do? What kind of, did it move the house? Did it shake pictures off the wall? These kind of things. And they did a program like that all over the western United States. It was as fast as a fighter. It had the long-range capability of a bomber. It had the capacity of a cargo plane. Okay? Which was way beyond what we'd had any time up to that point. The only plane that could almost keep up with it again was the B-58, and it was used as a chase plane for all tests. Typical flight, took off from Edwards and kind of went east towards Barstow and the Death Valley. They turned north, they flew up over Tonopah, western Nevada, up into southern Idaho, and then they would make a long right-hand turn over Idaho, Montana, Wyoming, Colorado, Utah, Arizona, and come back in. The B-58 flew on the inside so they could keep up with them. The B-70 was actually flying higher than the B-58, but at least there was a chase plane, and one member of the B-58 crew was always an XB-70 pilot so that they could watch what's going on. If there was a problem, they had a way to say, whoop, slow down, we got a problem. The best fuel economy they had was at Mach 3. Believe it or not. Remember I said, the faster you go, your fuel consumption went up. On this plane, it was actually the opposite. The faster you went, your fuel consumption went lower. They actually had better economy at Mach 3. As the B-70 went across the supersonic range, as it approached the supersonic range, Mach 1, the wingtips would drop down 15 degrees, and once they got above 1.5, they would go all the way down to add their capability a little bit more. The slide here shows the XB-70 is subsonic. Again, the wings are only down about 15 to 25%. There was another advantage here when the XB-70 was under Mach, the windscreen was down. Now there was a two-part windscreen. The cockpit had a windscreen, and there was another windscreen that would, as they would go fast, it would lift up on the outside, so it made the transition from the nose to the fuselage a lot more smooth. You'll see that over on the model over there. They've got it set up where it's actually at high speed. At Mach 3, the turning radius was 100 miles. That's the radius. Okay? It took 13 minutes to make a 180-degree turn. Okay? These were not necessarily designed for pinpoint navigation. At least not in a short range. They were definitely built for long-range type activities. In fact, one of the accounts I read said that they would be flying along between the different TACAN stations, and by the time the plane had locked in, they were already reading at 180 degrees, so they got to the point where they just started reading the 180 degrees out for the next one. One of the other accounts said that a lot of times they would be using the side windows to look for landmarks on the ground because the electronics were not good enough to actually show them where to go. They would be watching, even with the nose up, they could be looking out for different landmarks on the ground below them to make their turns. A lot of piloting by the seat of their pants, if you know what I mean. They couldn't even like talk to people. If there was like a control center where they needed to talk to, they only had about a 200-mile range from where they could talk to somebody. Well, if at 2,000 miles an hour, it only takes 6 minutes to go 200 miles. So if you got to get a real important message to somebody, it's not going to happen. Each mission required a significant number of support aircraft. If you remember the video up here, it shows that T-38 flying alongside it. Well, the T-38s were only one of them. They had the XB-70 T-38s. They used F-104s a lot, simply because they were faster. And they could actually keep up with it for a little while. The chase planes used to take off first. They would fly downwind, and they would set up a pattern away from wherever the XB-70 was taking off. They pull into the launch position. They would give a 30 seconds to launch warning. At that time, the chase plane would turn around and fly like the dickens as hard as they could to catch up, so that when that B-70 was ready to roll and take off, they would be right next to them. So these pilots had to do a lot of practicing to be right where they wanted to be at the time, because as that plane took off, the T-38s or the chase planes literally sometimes had to get up right underneath the engines and look to make sure everything was right, or they would fly underneath it. And they always had an experienced XB-70 pilot in the back seat, so they could look up in there and see what's going on, make sure everything was correct. One of the issues they had was the hydraulic system on this plane was very, very high pressure. Now, at subsonic speeds, using a low pressure hydraulic to move your control surfaces is fairly easy. But as you get really fast, the movement of air across your control surfaces is high enough that it takes an excessive amount of pressure to move those things. So they had a lot of problems with the pressure system. They wanted to make sure that any hydraulic pressure or electrical problems were identified early. The very first flight identified problems with the hydraulic system. They took off from Palmdale. They were on like a 20-minute flight up to Edwards. They were going to go up, and they were going to try to go supersonic, and then they were going to come back down. They got up in the air. They couldn't retract their landing gear. The hydraulics were not working properly, so they flew subsonic. They got up to Edwards, they landed, and their brakes locked up. Not a good thing. The hydraulics, and especially the braking problems, were, I don't want to say endemic, but they were something that they fought to overcome a lot. Sometimes it would blow out tires, sometimes it wouldn't. It was never really an issue, but it was not something that they could really take care of easily. By the time they came out with the second plane, the AV-2, a lot of the problems that they discovered had been corrected, again, because they had 13 flights to work on these problems and to test them and say, okay, if you do this, it'll work. Again, it didn't always correct everything, but it corrected most of them. One of the big problems they had with the hydraulic system was the main gear malfunctioned a number of times. One of the real classic ones was where the plane landed, and first I got to tell you, the landing gear and the main gear, when you see a commercial plane or most planes, when they land, the gear moves up like this underneath the plane and the doors come over. XB-70, okay, it's narrow, it's confined, it's not designed to have room for tires like that. So when the tires went up, they came up like this. And in order to do that, you've got your gear here and your tires are like this. The hydraulics, once they were in the air, the tires, the main gear would go like this, and then it would shove straight up into the plane. And it would then, the doors would close. One time, when they were coming back down, they lost hydraulic pressure, and the big hydraulic ram on the main gear, one side worked, one side didn't. So when they came down, the gear remained in this position. So instead of having all four wheels down here to hit the runway, they landed with two. Well, what that does is it kicks the plane up like this. So they landed on the lake bed out at Edwards, and they performed a nice long arc all the way around before they finally came to an end. They didn't land straight on. That particular incident highlights an interesting thing. They had a anti-braking system on this plane. And what it was a fifth tire. You had your main gear had four big tires, and there was a fifth one, a little tiny tire, between the bogies on the plane. And what that did was, as it touched down, it didn't have any weight on it, but it would spin and it would sense whether it was slick, whether it was wet, what kind of surface they were landing on, and that would help the plane to not brake or anti-lock system. Sometimes it worked, sometimes it didn't. Another time when they took off, there was an electrical malfunction, and the front gear with two wheels on it, instead of going up properly into the stow area, the door didn't close, so the tires came in and jammed on each side of the door, and they couldn't get it down. They tried everything. They tried landing hard, bouncing it, and trying to bounce it down. Nothing worked, because apparently the system had locked in, and they'd say, okay, that's the way we're going to be. It wouldn't do anything. Finally, one of the engineers down at Palmdale said, well, what we need to do is we need to bypass that electrical circuit. At the time, Colonel Joe Cotton, who was the program manager for the B-70, was flying, and he had to crawl around in back of the crew compartment. There was a little micro switch back there, and he happened to have a paper clip in his bag. And he took that paper clip and he shorted out the system, and the wheel dropped down and the door closed, and they were able to land the plane. If that hadn't happened, they would have landed it without front wheels, which could have been rather interesting. Sometimes when you're dealing with new technologies, particularly in the case of this plane, and the skin and the honeycomb system and that whole process, when you're dealing with new things like that, you've never had to deal with them before, things happen, things fail. The slide has a picture of a piece of the skin that has literally come apart. The honeycomb and one piece of skin is there, but the inside skin has come loose. They had to develop ways to say, okay, yes, this is a good weld, this is not a good weld, but they didn't know how to do that. They had to wait till something broke, and then they could fix it. The most significant incident that happened, though, was right on the front of what they call the splitter, which is the piece that is right in the middle, and the air intakes are on both sides of it. The splitter was made of that honeycomb material, and it failed one day and literally sucked all of that material as it came apart back through all 6 engines. Even though the engines were basically destroyed, they were actually able to save the plane. They made it back, but then they had to go back to the drawing board. Okay, now we don't want that to come apart again. What are we going to do to make it so that doesn't happen? So they had to develop a brand new solid piece splitter to keep that from going back down again. Now, every time they did that, every time they changed something like that, it changed the nature of the plane. So then they'd have to go back and test the whole process again to make sure everything worked. The final nail, I should say, in the program was the June 8th, 1966 accident. Congress had been looking rather dubiously at the XB-70 program for a number of years. They allowed it to continue simply because it was doing a lot of research. And it was doing research that couldn't be done anywhere else at that time. Leading up to that date, General Electric, who made the engines, had been talking with people in the Air Force for a number of years, or a number of weeks at least, about, hey, we would like to have a special permission to fly a photographic mission and just take some pictures of aircraft with GE engines in it for kind of like our publicity. And everything was kind of, well, talk to me about it next week, whatever. Finally, because this is something that had been done before with different manufacturers, different planes, let's get together and do this. Colonel Cotton said, okay, I'll check and see if we can do it. He asked his boss, and his boss said, I don't see any reason why not to. And because the XB-70, the number 2 vehicle, was scheduled for a orientation flight for a new pilot, it was a good day to do it, because whenever a new pilot came on, they were restricted by their speed. They could only fly a certain speed, certain height. So it was a good time to do it. The XB-70 was going to go out and do a mission, and all these other planes would catch up with it. They take the picture, go home, everybody's happy. They had a Learjet scheduled. It was owned by Clay Lacey. He was going to fly along and take pictures of the formation. He was going to have videographers. He was going to have photographers. He was going to have everybody on there. Everything was ready to go. They had a T-38 from Edwards. They had Colonel Cotton was flying in the back seat of the T-38. They had a F-4 from Point Mugu from the Naval Missile Test Center. And they had an F-104 from NASA. And they also had an F-5 from Edwards. F-5 is a one-seat fighter version of the T-38. They had them all flying in formation. Everything was working good. The XB-70 set up what they call a racetrack formation, where they fly a long distance in a straight line, make a turn, come back in a straight line, make a turn, come back the same, basically like a Indianapolis 500 racetrack. And each time they turned, they'd reform, take pictures. They actually took a number of pictures and everything was working good. Somebody said, hey, let's do one more run and we'll quit. So they turned, and they were just east of Barstow at the time, and they turned and they were coming back, and about that time they got a call from Air Control, said, you have a B-58 approaching your position at 50,000. So they were down around 20,000 feet, the plane was up at 50,000 feet, and they could see it coming, and everybody said, I've got it. I've got it. Everybody said, I've got it, except Joe Walker, who was flying the F-104. And about that time, whatever happened, I'm not sure. There's been arguments about what happened, but his left side tip tank hit the wing of the XB-70, and what it did was it pushed his plane like this, and then air hit it, and it pushed him across the back of the XB-70. It took out both vertical stabilizers, killed him instantly, and basically had a fireball flying off the back of the XB-70. It also rolled over and damaged the left wing on the plane, so that really there was no vertical control system. And I was talking with a gentleman earlier this morning that said that a lot of the controls in the vertical stabilizers were your rudders and things that were controlling things. What happened next, though, was that everybody scattered. Now, if you're thinking about it, you're flying in formation, something happens over here, everybody goes this way, what's your first tendency? turn this way to get out of it. So it's amazing that when that happened, the F-4, which was flying on the other side of the plane, didn't hit the T-38. So this could have been a lot worse than it was. Somehow they all got out of the way. The XB-70 continued flying flat level for about 13, 16 seconds. At that point, Al White, who was flying the B-70, said that it started to crab sideways because it didn't have vertical stabilizers anymore. It started going sideways. And as it went sideways, he started to correct. He didn't know he'd been hit. He heard all this chatter on the radio about midair, get out, eject, but nobody said, Al, the B-70's been hit, get out of there. So he didn't know what was going on. All they heard was a thump. They didn't know what was going on. So as it went along and it started to crab sideways, he put in the corrections, and as soon as he put in the corrections, the plane flipped over and rolled down. Just a snap roll. At that point, he was fighting the inertial forces. He was trying to get control of the plane. The plane eventually came back up and went into a flat spin. And as it went down, it started coming apart, literally. And what he did then was, of course, the eject sequence is grab that thing, pull the clamshell down. Well, unfortunately, it's hydraulic actuated, so when it started, he didn't get his right arm in fast enough. So that clamshell came down on his arm. So it wasn't closed, the door wasn't closed, so it was down there and he was trying to fight. Okay, if he'd ejected at that time, he would have lost his arm. So he was fighting this. He looked over trying to get his co-pilot to, eject, whatever, and he said all he could see was the co-pilot's head was just moving like this, like he was unconscious. So apparently when they went that first snap, it did something. And we've discovered since then, when Dale Earnhardt was killed in that accident, it was a very minor movement that killed him. And it's very likely that something in that same situation happened to the co-pilot. He eventually got his arm free. He was able to complete the ejection process, but he didn't close the door properly. Now, on the bottom of this injection seat, because it was small, there was a cramped space, they decided, well, we'll put small parachutes on this thing, and we'll put a flotation / cushion on the bottom of it. It's air, so it'll hit and it'll kind of help, okay? Well, that air cushion only activated if the complete process had been done. So when he ejected, because his door didn't close properly, that cushion didn't inflate, so he got kicked out through the top. He said all he saw was this big monster went whoosh underneath him as he went by. And then the plane kind of went this way, and he was following it down, and the wind caught him, kind of pushed him away. His parachutes came open, but he was falling really fast. When he hit, he said that his heels were imprinted in the bottom of the capsule, and there was an imprint of his buttocks on the seat, in the metal seat underneath that he was sitting on. So he landed with very, very significant force. He survived, but he was in the hospital for a long time in very, very serious condition. Now, as that plane went down, as it kind of settled into that flat spin, as it's going down, literally ripping pieces of that aircraft off. And Joe Cotton was following it down as far as he could, and he was calling out, there's stuff flying by. Literally, little pieces of that plane were flying by and were fluttering down. The debris field where the plane landed, where it crashed, it landed flat on the desert, is fairly small. But the debris field from all that stuff that blew off is huge, way up there. And that's where they found the piece that's over here, was actually away from the crash site. The plane came down about 11 miles north of Barstow. Al White came down nearby. It wasn't too far away from the plane. Where Joe Walker's F-104 came down was in about that same proximity. They kind of came down together. It was kind of a mess. One of the things that we've learned over the years is that, okay, if somebody makes a mistake like that, what do we do? Well, in this case, there was a lot of political, pointing and naysaying and all this. I'm not going to get into that because really, it doesn't help. One of the big things that did come out of this, and is probably one of the more effective outcomes, was that the Air Force actually came out and said, okay, look, I know that you've been doing what you've done. You go out and take pictures, you do all these things. We've got to tell you that we can't let you do that anymore. So there was a policy in place that said if a company wants to take pictures, they can take pictures, but it has to go to the Secretary of the Air Force for permission. Nobody really paid attention to that. It had been done for years, and basically what they said was, no, we can't do that anymore. We have to have higher level of permissions on these things because we've got to control this. Because if you don't control it, if something happens, what are we going to do? What are we going to say? And there was a large negative reaction to this whole thing. And in fact, this was in 1966. By 1967, the Air Force had given the plane to NASA. They continued doing some flights, and then NASA turned the plane over to the National Museum of the U.S. Air Force in 1969, where it sits today. That really kind of is the end of my briefing about the XB-70, because really it went away after this. It was kind of a non-player. However, all of that data that was collected over all those years has found its way into other uses. A lot of it was used in the Apollo program, believe it or not. And if you take a look at a model of the B-1, you'll see that same really long nose, but a lot of the technology that was developed in the B-70 is now evident in the B-1. And a lot of that stuff that has been studied and worked on back then is still available, and they're actually looking at this stuff and applying it to new technologies that are coming out, simply because it's there and we can use it and it's available.
Thank you for watching Peninsula Seniors Out and About. I'm Betty Wheaton. See you next time.